finding the inverses of nonlinear functions. So the first problem in class notes asks us to find the inverse of this function. And during freshman year, you already learned how to find the inverse. And there's 3 steps. Step 1 is to switch the x and y. Step 2 is to isolate the y. And step 3 is to rewrite the function in inverse notation. So when I look at this problem, I don't see a y. And for those that I've forgotten, f of x is the same as y. So let's go over the top of f of x and just write a y. So step 1 says switch the x and y. So wherever I see a y, I replace it with an x, and vice versa. Wherever I see an x, I replace it with a y. So I'm done with step 1. Step 2 says to isolate the y. So we want to essentially solve for y. We want to isolate it and have y as the only variable and the only thing on one side of the equation. So I want to get rid of the -1 and the square root. Now to get rid of the square root, I could just square this if you recall, because to cancel out a square root, you square it. So remember what you do to one side, you must also do to the opposite side. The square and the square root cancel, and I bring down what was underneath the radical. And now I'm going to add 1 to the opposite side. Plus 1, plus 1. So I've done step 1, and I've completed step 2. Step 3 says rewrite this. So we need a way to denote this function as specifically being the inverse of this original. So to do that, we're going to write down f of x, and I'm going to write down this answer, x squared plus 1. And now to denote this as the inverse, we write an exponent of a -1 for the x. This means that this specifically is the inverse of this original function f of x. Please help me out. Thumbs up, I understood. The side I'm a little confused, down as I'm completely confused. Okay, do second plus 7, 1, 2. The second one says, what is the domain of this inverse? So here's the inverse function, and we want to write the domain. So grab your calculator and please do second plus 7, 1, 2 to clear the RAM. Now go to y equals, type in x squared plus 1. When you're done, graph it. We're looking for the domain. Although we don't see it on the calculator, remember there is an arrow here and there is an arrow here, meaning that as it moves to the right continuously, it's also going up, and as it moves to the left continuously, it's also going up. There's no limit how far this will continue to move to the left as it goes up, and there's no limit how far this will go to the left as it continues to go up. So with no limits, in interval notation, we would say the domain is -infinity to positive. Sometimes it's a little more difficult for students to understand, so please turn to your partner and make sure you both understand how we identify the domain. 10 seconds, go. Santos, your partner wasn't here, so you're going to have to help out a little more today, okay? Got it, Santos? Santos, do the music in? Take it out, please. Okay. Nayeli, your partner wasn't here, so you have to do a little more work with her too when we get to some of the problems, okay? Okay, here we go. This is the problem that most students struggle with. It says we need to prove, another word is verify. You may see the word verify. We need to prove or verify that f and the inverse of f are inverses of one another using something called compositions. compositions require you to be very detailed in how you show work. And this is the concept I spoke with before we started filming. This used to be a separate lesson in Algebra 3 and Algebra 3 Honors, or Algebra 4 and Algebra 4 Honors prior to Common Core. And now they don't include it anymore. But we still need this concept in order to prove that they are inverses. So what I want you to do is put your pencil or pen down. I want you just simply to watch. And then when we are done, I'll have you write it down. This also ties into number 4 for it to really make sense. So composition functions, how this works. I'm going to write f of x, but instead of writing x here, because normally the x would go right here, correct? Inside. I'm going to put f on the outside, and on the inside, I'm going to write the inverse. Now what the heck does this mean? I need to have space here to do two problems. Okay, this means that I start by writing down what f is, but wherever I see a variable, I'm going to leave an open parenthesis. So the original f function was, I'm going to come back to that in a second, was the square root of x minus 1. But I'm going to leave a parenthesis where I see an x. Now in that parenthesis, I need to put on the inside in that parenthesis what the inverse of x was, what that function was. And that function up above, if you look on number 1 right now, you don't have to have a pen, look at number 1, that function was what? X squared plus 1. Okay, now my goal is to simplify this as far as possible. So when I look at this, a positive 1 and a negative 1 are going to cancel under the radical. And a square root and a square are going to cancel. And I'm simply left with x. And we're going to explain the significance of that in the next problem. Okay, now I need to do the opposite. So now I'm going to start with, let me move this over to the side. Now I'm going to start with the inverse on the outside and the function on the inside. So what does that look like? So I look, first of all, what was the original equation for the inverse? It was x squared plus 1. Remember, wherever you see a variable, you're going to leave it blank with a parenthesis. Inside that parenthesis, I'm going to put the equation for the f of x function, which was the square root of x minus 1. Okay, let's simplify. The square root and the square cancel out, and I bring down x minus 1 plus 1. The minus 1 and the plus 1 cancel out, and I simply bring down x. We just verified or proved that the function f of x and the inverse of the function f of x are inverses of one another. And I'm going to explain why in number 4, why this is significant, okay, why we get an x. All right, write this down, let me zoom out, and then we're going to go on to number 4. your hand if you need more time to copy this down. Okay. Luis or Jesus, do you need any more time?
No.
Henry, are you okay? A little more time? Okay. Let me know when you're done. You see good? Okay. Excuse me. Let's go up to number 4. Number 4 and number 5 are going to relate to number 3. So we are going to graph both f of x and the inverse of x. And we may need to put some restrictions on the input values, but let's start with f of x. So can everybody write down f of x equals the square root of x minus 1? And your initial reaction may be, how do I graph that? Okay, on Thursday we learned how to graph square root functions. So remember, if there's nothing behind here, it's really like a plus 0. If I asked you, how do we translate this from the original parent function? That means how do we shift it? You'd say shift it once to the right. Don't shift it up or down. So let's go once to the right and make a dot. This is like my new, I'm going to do a different color here so it stands out. This is like my new origin. Now we could make a table of values if that helped you and we could graph from there, but if you remember the pattern, it's 0, 0, 1, 1, 4, 2. Okay, so here we go. From here, I'm going to go over 1, up 1 for 1, 1. Go back to our new origin. I'm going to go over 4, 1, 2, 3, 4, and up 2. And I'm going to count over 9, it's a little off the graph, and up 3. If you have forgotten how to graph a parabola, this is a simple parabola that we are just going to shift up 1 unit. So think of our original parabolas. If you've forgotten how to do that, we can come over here and we can make a simple table. And by the way, are we allowed to plug in negative numbers and square them? Is that allowed, or are you breaking a math rule? No math rules are broken. Like for instance, what's negative 2 squared? 4. And 4 plus 1 is 5. Negative 2 or negative 1 squared is 1, and 1 plus 1 is 2. 0 squared is 0, 0 plus 1 is 1. 1 squared is 1, 1 plus 1 is 2. 2 squared is 4, 4 plus 1 is 5. So let's graph those 5 ordered pairs. We probably could even add in a 3 here. If I did 3, 3 squared is 9, 9 plus 1 is 10. I'm going to come up here and I'm going to write down the ordered pairs for what we see in red. So we started at 1, 0, and then we went 2, 1, 5, 2, 10, 3. Okay, so if you recall from number 3, I said this was going to play an importance, and you learned this freshman year, and again we went over it in the first few units of this year. So does everybody see we have a function equal to x here? Function equal to x. I want us to graph the equation. Let me go where everybody can see this. I want us to graph the equation y equals x. What does that mean? It means every value you plug in for x, you get the exact same value for y. Watch. Plug in 0, I get an answer of 0. So it goes 0, 0. Plug in 1, I get an answer of 1. Plug in 2, I get an answer of 2. Plug in 3, I get an answer of 3. It does the exact same going in the opposite direction. Negative 1 is equal to negative 1. So please, using a pencil or pen, I want you to make this dotted line throughout the entire coordinate plane. Okay, now I'm going to ask you a difficult question. Between you and your partner, you're going to have a full minute to do two things. Looking at this graph, along with the ordered pairs that you see, looking at this graph along with the ordered pairs you see, I want you to analyze it. And I want you to come up with two things that you notice. Two significant things. I'm giving you hints. One will be about the graph and one will be about the ordered pairs. Talk with your partner right now. 1 minute, ready, get set, begin, go. I hear Jesus saying one. You're talking to your partner. Whisper Jesus, please, not over here. Be more specific of your explanation. I'm consistently hearing one of the same as I walk around. Jesus, can you explain, since you were the first person that I heard state this comparison, can you tell me what you noticed about the ordered pairs? And if you're curious, I'm describing this as an ordered pair. Describing these as ordered pairs. Okay, go ahead, Jesus.
Just say you get a point from the parabola.
Okay. So can I just choose one? Okay, so Jesus, if you didn't hear, said choose 1 point from the parabola. So I'm going to choose this one right here, which is 5, 2. Okay, I got it.
And if you flip the x and the y,
so if you take the 5 and 2 and switch it to make it a 2 and 5,
it's going to be the same point, but on the
so I find 1 point on the parabola. If I flip it, then I actually find it on the radical graph. Nice job. Let's try that again. So 10, 3. 10, 3 is way up here. If I flip it, I have 3, 10 here. Does everybody see that? But here's the thing. That's great. That's great. Does that occur for every single point if you look at the parabola and you look at the radical we graphed? Is that true for every single point? Okay, let's check. It's true for 2, 1, and 1, 2. It's true for 1, 0, and 0, 1. But is it true for negative 1, 2? Is that up here? Okay, why is it? Look at this function and look at this function. Talking about breaking a math rule. Can you break a math rule by plugging in, inputting negative numbers to a number you're going to square? No, because we can square a negative. Could we break a math rule by inputting in numbers underneath a square root that are negative? Because we can't take the square root of a negative, unless we're going to get imaginary numbers, but this is not imaginary, we're only talking about reals. That's why this particular function, this parabola, we have unlimited number of points we can get. Okay, that's why it has two sides here to it. But this particular function only has one side because we're limited on what values we can plug in. So I would like you to draw a little arrow here off of this function. And we can plug in here 0 or above. Does everybody see that? Okay, so we're going to say for x values that are greater than or equal to 1. And then I want you to come over here and I want you to just cross out what you see. Anything to the left of 0. So now I am only looking at, let's see if I can darken this in. I am only looking at this part and at this part. I need one more comparison that you can see between the two. Thank you for your help, Jesus. Anybody else? Yeah. Okay. Nayeli is describing it, and then I heard, I think, Lois say the word reflects. Do you guys see how they're reflective? If I asked you to go along this pink line and fold your paper over, you would see that the red line actually lays right over the top of the blue line. So please come down below. There's two things we need to describe. The first is this function, f of x is equal to x minus 1, and the inverse, which is f of x is equal to x squared plus 1. But there's a key here. We have to say where x values are greater than or equal to 1. These two functions, with this limitation, reflect across the line y equals x. And actually, that will happen for every single function. Every single function, if two functions are inverses of one another, they will reflect across the line y equals x. Sometimes you're going to have to put limitations in. That's true. Limitations on the input values. The second one is I want you to write what Jesus talked about. Assuming that we have a limitation on this function, I want you to turn to your partner and how can you describe the coordinates of one function related to the coordinates of the second? Okay, talk about it. After you've gathered your thoughts, then I want you to write down your explanation down here. So the x and y coordinates of one function become the y and x, right? They flip and become the y and x coordinates of the second function, or vice versa, okay? So the x and y coordinates of one function become the y and x coordinates of the other function. Number 6 and number 7 are more practice with verifying or proving that two functions are inverses of one another. So as you recall from number 3, if they're inverses, after you do all the work, you'll have your function will equal x and your function will equal x again. If for some reason one of these does not work, the two are not functions of one another. Did everybody hear that? So let's talk about this. Let's say you do the first one, you get an x, and the second one you get like an x plus 1. Are they inverses? But on the first one you get a 2x plus 3. Do I even need to take time to do the second one? No, because the whole point is prove or disprove that they're inverses. You need an x both times. So on one chance, if you don't get an x, don't bother doing the work to prove the second one. Okay, so we're going to use composition. I know I don't have a lot of room here. We're going to start with number 7. Number 7 is very similar to number 3. So can you and your partner please look over number 3 right now? I'm going to give you 30 seconds to analyze it. Number 3. Okay, with your partner, I need to hear nonstop talk. When I say go, you're going to start. You're going to have a minute and a half to do number 7. Your whole goal is to verify or prove, are these two inverses of one another? If at any point you're confused, you look up, and I'll be doing the problem as well. Or when you're finished, look up to see if you have the same answer that I do. Okay, you ready? Minute and a half. Need you talking the entire time, and begin. Does anybody have questions for me about this problem? Okay, do me a favor. I understand this is difficult and it's a lot of detailed work. Can you do a thumbs up or to the side or down just so I know where we are? Most of us are to the side or up. Totally fine to be to the side. We're going to get more practice. Remember, not every single problem is going to work so they are inverses. This problem reminds me a lot of number 8 from your last checkpoint quiz. Okay, you're going to do this problem with me at the same time. So I'm going to write down A, and I'm leaving a blank parenthesis wherever I see a variable in the function A of x. Then into that blank, I'm going to substitute the function B. And then the confusion started with my previous class. They said, well, can't I just cancel out the radical and the square? Can't I just square -2? Because there's two things inside, this says rewrite this portion twice. So let's do that. Rewrite it twice. And now we're going to FOIL. Remember that FOIL is front, outside, inside, last. Also remember, as an example, when you take the square root of something times the square root of that exact same thing, like square root of 3 times the square root of 3 is simply 3. Square root of x times square root of x is simply x. Okay, so here we go. Multiplying the fronts for FOILing. Square root of x times the square root of x is x. Now O for outside. So the outsides would be the square root of x times -2. Square root of x times -2 pushed together to get -2 square root of x. Insides, exact same thing. -2 times the square root of x, again pushed together. And last, -2 times -2 is 4. Don't forget to bring down the +2. Okay, let's combine like terms. There's no x's by themselves, so I bring down x. I can combine -2 square roots of x and -2 square roots of x combine to give you -4 square roots of x. And 4 plus 2 is 6. There's nothing more I can do to simplify this. So is this answer simply x? No. Since it's not x, I don't even need to go to the hassle of doing the second time because we need to get an answer of simply x. If it's not, I can state that A of x and B of x are not inverses.